the integral of the floor of the exponential function from 0 to the natural log of x. Let's look at each part individually, starting with the exponential function. E is just a number, roughly 2.718. The exponential function raises this number to various powers. Now, let's plot these values on a graph. The horizontal axis is the power, and the vertical axis is the value produced. However, we're not limited to just the integers. Any real number can be used as the power. This is the exponential function. Next is the floor function, which is the same as rounding down to the next integer. So how does the floor function affect the exponential function? Every point not on an integer drops to the integer directly beneath it, therefore splitting the curve into a series of horizontal sections. Now, on to integration. For any function, the integral finds the area under the curve. The horizontal boundaries of the area are the limits of the integral. They sit on the integral symbol, with the rightmost boundary being on top. The goal of our problem is then to find the total area of all of these rectangles. To start, let's label our diagram. We'll mark the x-coordinates with alphas, where the index marks the first time the function hits that value, i.e. alpha 2 when the function first hits 2. For the areas, we'll use a's, where the index counts the rectangles. But what are the alphas? When x equals alpha I, our function outputs I for the first time. Because the exponential function is always increasing, e to the alpha I equals I. Therefore, alpha I is the natural log of I. This pattern will continue until the x-coordinate is the upper limit of the integral, the natural log of n. Thus, this pattern continues until alpha n. We can use the end of this pattern to find out the index of the last area. The index of each area matches the index of its bottom left corner. Therefore, the index of the final area is n-1. Let's now work out the values of these areas. Each one is a rectangle, thus the formula to find the area is base multiplied by height. The heights are given by the index of each area, and the width is given by the difference between two alphas, one with the same index as the area, and the other index is one greater. Expanding the brackets produces this horrible expression, but shifting the left-hand terms down by one row makes it much easier to deal with. Each row results in negative alpha I, apart from the last row, which contains n-1 lots of alpha n. Expanding this bracket produces two terms. Negative alpha n completes the pattern, and for now, n alpha n can be put up here. Let's factorise out the negative, rewrite it in sigma notation, and replace the alpha I with log I. Now, the log laws state that the sum of logs of elements is the log of the product of those elements, which as our elements are the numbers 1 to n, the product becomes n factorial. A few more applications of the log laws brings us to our final answer, the natural log of n to the power of n over n factorial, which I think is beautiful.